So I asked you last time to finish up that power law model, power law fit. So let's just quickly review how is it going. So our code for linear regression was simply, let me get to we had the exercise where we simply coded up linear regression. So basically our code was simply computing these coefficients A0 and A1 that are attempting to do a straight line with coefficients A0 and A1 through the data. Okay? And you basically do all kinds of sums with the data points. And you take a for loop and you compute all of those sums and you compute A0 and A1. So when we do that, we actually created a function that does so. So my linear regression function, x and y, is estimating the length of one of those vectors, and hopefully both of them have the same length. I'm not checking right now, so this is a bit of a poor programming practice. So then I set up all of the sums to go from 0, and in for loop I keep adding to them. And again here I can use plus equals to, that's equivalent to writing sum xy plus equals to this element is the same as writing sum xy equals to sum xy plus this element. So this is just two different ways to do that. So this is a shorthand notation. And then I just compute my A0 and A1 based on the sums. Great. So we have all mastered that last time. I have also added something called R square. And this is our estimate of how good the fit is. That was hiding on this slide that I showed last time. So this, using the similar type of sums, I need only one more. I also need sum of y squares, which I additionally didn't compute. But I added it, and I computed this R. We typically report R squared. So this is sort of like how good is your fit? And you essentially, and this number is less than 1. 1 is a perfect fit. So if I had data that is all lined up on a line, and I estimated what that line is, I would get R squared of 1. Okay. And then it goes below that for a little bit more scattered. We typically look for R squared of 0.8 and above, okay, for a good fit. So let's actually quickly see how does R squared work for this data. So if I actually do run this linear regression, and I can also print, I'm printing R squared. I'm going to comment this one for now. So if I print my R squared, I see that it's about 0.75. So it's not too good. Okay? And we can also see that from our linear fit, this data has, like if I run a straight line, it's not the best representation of this data. Okay? Now, I asked you to do power law fit because we obviously have some curviness to the data, so some sort of a curved function would do better, and power laws typically fit into that category. So if I assume that my data model is y is some coefficient a2 times x2 b2, so this is power of b2, and I'm looking for a2 and b2. I can linearize this problem so that I actually take a log. This is an actual log of both sides. Log of y is the same as log of a2 plus b2 log of x, because b2 was an exponent. Right? So when I actually look at that, I can see that I actually have a linear relationship between log of y for all of my y points and log of x. So this is my new set of data. Okay? And that set of data seems to have a linear fit, and I can estimate those A0, I call that capital A0 and capital A1. So I can compute them, and when I do, I can find A2 by basically taking just exponential of A0, because log of A2 is A0, and B2 is simply A1. So with that, my power law model based on data x is a2 times x to the b2, right? So if I plot this model, power law model, against the data and compare actually both the linear regression, so I can plot my original data, x, y, and then x and y model, which is, this is my linear model, is 0 plus a1x. And also this power law model, x and a2 times x to the 2, I will get something like this. So those of you who have submitted the quiz, have you gotten something like that? So obviously this green curve, I can actually label them. How's that done again? Label as linear model and label as power law and then PLT legend. Okay, so my linear model and power law model, obviously power law tends to follow the data much better. So I can see that visually. Let's see how my R2 works. So basically I can see how this model had an R2 fit. Let's actually print that number and see whether it's better. So yes, it's 0.95 if I round it up versus 0.76. So obviously my power law fits the data better. So R square is the measure of the data, or how does your model fit the data. Whenever somebody shows you the data and the fit to the data and just shows the line or whatever it is that they fit it, ask them what is R square. So if R square is not above roughly 0.8, it's not a very good fit. You can still use it, but you should be aware that it's not a very good fit. It's still a correlation that roughly follows the trend. If you needed a simple linear trend based on your data, regardless of how bad it might be, you can still use it, but you should be aware of that. And often when you have a very scattered cloud of points, just running a straight line through it, it's not a good thing. You can still do that because if it's a cloud of points, it's not really correlated actually at all. And there's no line that can do a good job through it. But so you have to be aware of that. You can make that a mistake, but please because sometimes you just don't have a better option, but be aware. So ask people for R square, and whenever you are actually reporting a fit to the data, please report R square. Okay? For transparency. All right. So we can have a lot of different nonlinear types of models. So I could, for instance, in the if I have or attempt to fit something like the first equation. So I'm choosing a model that is a times exponential to b times x. I would again do log of both sides, and then I would get a relationship between this is my new y and new x, so new sort of data. So data, this x and ln of y are in a linear relationship, and these are the coefficients. So if I run them through linear regression, then this is my first exponent, which I called a0, and this is my second exponent, which I called a1. Okay? So if I find them, then I can find a and b based on the fact that this is equal to a0 and this is equal to a1. Does this make sense? So we are using linear regression and our code for linear regression to basically estimate nonlinear fits. And the reason why that's important is that it's way easier to do that if I actually went through the procedure that we went through at the very beginning of the worksheet. And for those of you who weren't here, I did post the worksheet into the files on Canvas, so you can have it for reference and work through it on your own. So basically, I can go through that procedure, but instead of the system of linear equations, in that case, I would get a system of nonlinear equations. And that's much more complex to solve. So it's very good if I can actually figure out how to linearize my nonlinear relationship, okay, and get a system of linear equations. So this process of fitting, so most of the time, if I actually ask you in your test to do a nonlinear fit of a nonlinear function to your data, you have to go through the process of linearization, such as these two. So look at the function and figure out either taking a log of it or some sort of algebra of how to transform it into a linear relationship. Okay? And here is a list of nonlinear equations and sort of linearized forms of those equations that you could have. Okay? But the procedure is the same as we just did and as we did on the. And again, this is approximately how my data fits, linear fit and power law. Okay, we can have, you pretty much know the gist of curve fitting. Now it's just, the question is always, what are you trying to fit? What is the functional form that you're trying to fit your data into? And you could, in some cases, attempt to do multidimensional things. So you can have two variables and basically looking at z or y in this case is a function of x1 and x2. Okay. So I'm trying to estimate a functional relationship of that type, or you could try to do a polynomial. So there's multiple things you could do. The procedure is always the same. I figure out what my model is. So here's an example of a polynomial. Here's a polynomial. Obviously, if I have something very curved, a linear straight line through the data will not do. But in this particular example, a parabola or something parabolic would really work. And in that case, I'm going to look for a0 plus a1x plus a2x squared. Okay. In this case, fitting a polynomial, I can go safely through my standard procedure. I look at the sum of the squared residual because there's nothing nonlinear in terms of a0, a1, a2. All the nonlinearity in this model is on x. Okay, so I have x squared. So I don't have a0, a1, a2. There's nothing weird happening there. They're like linear terms. So those cases, I go through my standard procedure. And I look at the sum of the residuals, and I'm going to try to minimize that sum. And I know for the minimum that partial derivative of this sum with respect to a0 should be 0. Partial derivative of SR with respect to a1 should be 0. And then partial derivative with respect to a2 should be 0. So that's going to give me 3 equations for 3 unknowns, a0, a1, a2. This is procedure just like the one that we did on the worksheet, and you should be able to do it on your own if I asked you to. So when you actually work that math through and sort it out, then we actually get a 3 by 3 system. Okay? And my unknowns are a0, a1, and a2. So it's again a bunch of sums. So in this case, I would not just, this is the portion that we had for the linear regression. Now I'm getting one more equation and one more unknown. Okay. So basically the sums that I need to compute are also cube xi cubes, xi to the 4, and also xi squared y, and xi y I already have. Okay. So in that sense, I'm just setting up a 3 by 3 system and solving for a0, a1, and a2, and finding those. So this is how I would get a parabolic fit. Okay? So this is a least squares parabolic fit. I could also do multiple linear regressions. So basically I have dependencies on 2 variables. So for instance, variables x1 and x2. So again, I just set up what my relationship should be. So if I'm trying to fit a plane through the data, that is a cloud of data in 3 dimensions. Okay. Fitting that plane is essentially this description. Okay. And I just basically set up my SR the same way again. And in order to fit this plane, again, partial derivatives with respect to A0, A1, and A2 have to be 0. I set them to 0, clean up the equations, and this is setting them up to 0, and I should get something like this. And again, I set up this linear system, and I solve it for A0, A1, A2, for instance, with np.lineout.solve or Gaussian elimination that we developed in class. And then I'll get those fits. Again, procedure is very similar. So on your final, I might ask you to, for instance, derive either this one or that one. Okay. In summary, what we're aimed to do here is having a bunch of data. We need to some sort of estimate a functional form that this data conforms with. It's not necessarily perfectly going through, but the way I set that up is that I look at the error between my actual data point and my model. I set up what the model is, and I look at the square of this difference between the two. Those are square of residuals, and I'm trying to minimize this sum. Okay? I set the partial derivatives equal to 0 and figure out what my system, linear system is for the unknowns. Hopefully it's linear system. And for example, if I wanted a straight line, I would get basic formulas for this straight line based on the data. Okay? And that's what we programmed in class. So this essentially ends the curve fits. Curve fits, a lot of times, you're going to work, if you work with massive data, then you should probably work with a programming environment like Python. If you work with smaller data sets, there is actually, and you're looking at through it in Excel. In Excel, there's literally, you click on a little button, and you will get a line through your data. It should also give you what R-square is to see how good it is. So you can use that, like you can use those lines. And there's a couple of different options in Excel where you click on it and you get the estimate. So you will kind of use that a lot. Okay? But now you actually know what's happening behind when that curve fit is computed. Okay. All right, without further ado, we are starting our last topic, and that is ordinary differential equations. Your favorite topic, right? Right? Especially after this project. Not only that you love differential equations, you love partial differential equations, right? Multivariate stuff is always more fun. All right. So our last topic is ordinary differential equations, but fear not, I will not ask you to solve any ODEs. That you do in a different class. And what you mean by solve there is find an analytical, functional form solution that satisfies a differential equation. That's not what we're going to go here. We're going to here discretize differential equations. And what that means is that we're going to find a set of points. Okay? And for that set of points, I'm going to find approximation for the value of that function at those points, and those points only. That's what numerical methods do. So I don't necessarily find a closed form functional solution. That's the stuff that is in theory and in basically analytical solutions to these equations, and is very valuable if you can actually get that closed form. However, you can really find analytic solutions for something like 2 to 5% of all of the problems you want to solve. The set of problems like you got in your project, there is no analytical solution. None. Okay. You gotta look for it numerically. Maybe there would be one if that permeability field is same everywhere. I don't know of a reservoir where that is true. Okay? So reservoirs typically you can find them with variations in porosity and permeability, okay? Such as life of a petroleum engineer. And there's just nowhere, or any kind of subsurface engineer, environmental and petroleum. So you always have variation in these porosity and permeabilities, and you will rarely have analytical solutions. In certain simple cases, you might have an analytic solution that you can find, but in most practical cases that actually apply to some field that you know, you need to go numerical. So we need to discretize these differential equations. And here we will just actually scratch the surface of how do I discretize a certain set of boundary problems. So let's get going. Here is my example where I don't have analytical solution. So let's assume that I have a water tank, okay? And I'm trying to empty that tank through this faucet down there. Okay? So I have a certain influx that might have, for that I might have some functional form, or I have data. So stuff is coming in at a certain rate, and I have rates of it coming out, which kind of depends both on the geometry of this hole here, how wide is it, and it depends on the pressure here that I have, and pressure depends on the height. But if I have stuff constantly coming in, that height is constantly changing. So it's something that is extremely hard to put a finger on in one go, so I have to kind of dynamically solve it. Okay? And this is where numerical solutions come in. So what do I have? I have that my water flow into the tank is actually given, and it has some variation to it that is like a cosine. And let's say that I know all of these. I know K1, I know K2, I know C. And then the water flowing out, there's actually, I can calculate it, and it's related to the height, h, of the column, okay? And to the geometry of this area here of the pipe or hole that comes out. Okay? So this is my rate of mass flowing out, rate of mass flowing in. I need to balance the two, okay? So change of mass in the tank is basically just the difference between what's coming in and what's coming out. So I can balance that, okay? And the change of mass inside is basically change related to the change in height, because I know the geometry of my cylinder, and I can relate mass is rho times volume, and volume is area of the tank times difference in this height. So this change in mass is related to the change in height in this tank, and this is my differential equation that governs height of the water in this tank based on what's coming in and what's coming out. Okay? So this does not look like something I can find necessarily analytic solution to. I have both T here and H here, right? So that can be a problem. So basically, if I solve this differential equation for H, starting at some time is equal to 0, then I actually have a solution for the height at any time, or a close to it. So how do we do this numerically? Before we actually get into how do we do this numerically, let's just quickly review our notation and how do we call things. So in this case of a tank, I would be given certain initial value for this tank, height in the tank. Like, what was it before we actually started flowing? What was the height in there? That's a measurement that I had. Okay, that is my starting point, and then I turn on the faucets and get going. And I want solution from then on. Problems like that are called initial value problems. The problem that we actually already discretized, which was our linear system example, because we ultimately got a linear system for it, is called the boundary value problem. That was my heated rod that had temperatures set on both sides of the rod. Another boundary value problem is the one that you got in your project. Okay? So that class of problems has its own way of discretization that you ultimately end up with a linear system to solve. So that we kind of already handled. And here we are going to focus with these initial value problems. So they typically have some, and we're going to really look, for the most part, with first order and second order equation. So when I have an equation of the form dy dx is x squared plus 3xy plus 4, or if you want the dy dt is y squared plus 3ty plus 4, or second order equation d squared y dx squared is equal to 4. So order refers to the order of the derivative that I actually have in the problem. I could also have partial derivative equations. We're not going to handle them here, but you have them in your project as an example. So if you have a function that depends on multiple spatial variables, then you can have partial derivatives, and you need to solve those as well. So we're going to here focus on these initial value problems, basically of the first and second order. So let's, as an example, set our notation that we're solving something that is dy dx is f of x, y. So this function on the right-hand side could have both the value of y, which is the function that I'm looking for, and x, which is the variable in the problem. So how do I solve this? Okay. So the simplest way to solve it is to iterate in some way. Iteration we already know. Those are our favorite examples of for loops. So what if I actually, I'm starting from a value. So I have, this is initial value problem. So one of these boundary conditions is given as a starting point. For some x, I have a starting point, value y. So now, from there on, I want to step-by-step iterate. And how I'm going to do that? The simplest way is always linear. So I'm going to start with my old value of yi, right here. And I'm going to estimate my new value, which is at my next point. So what I'm doing here, I'm actually discretizing, which is not shown here. And hopefully this works. But this is my x0, x1, x2, and so forth. So see, here I am at xi. I have a certain value yi. And I'm looking for what is the value of y at my next point, xi plus 1. And I'm going to do that in the simplest case by saying, hey, it's yi plus some slope, phi, times difference in x's, which is what I typically refer to as this difference here. Okay? And where is that coming from? Okay. So I have some xi plus 1. Okay. So it's coming, this is my slope phi. So I'm basically estimating the simplest thing that I could do is look at the value that I currently have. So this is xi yi at this point here. And I can look at the derivative of function y that I have at this point. What is dy dx? Based on my starting problem, what is dy dx? Here might be close to 0, but what it is up there based on the first equation that I'm actually solving. Dy dx is equal to f of x, y. So at this point, I have xi and yi. My differential equation is telling me that the slope dy dx here is f of xi yi. Because that's what I'm solving. So I have estimate for the slope at this point based on the way this differential equation is formulated. So dy dx is simply the slope, right, of function y. It's y prime of x. Yes? So that's the slope at this point. And at this point, I have it estimated by f of xi yi. So I'm going to take that slope that slope to the next point it takes me doesn't take me very close to the actual equation in this particular point, but this is one way to do it. Okay? And if I don't go very far, like I do here very far, if I don't go very far, I might be actually close to my actual y, this, assuming that this is the y I'm looking for. Okay? So that is basically taking the step size as h, and then just multiplying by slope. I'm going to get this value of yi plus 1. Quiz. Where is this coming from if this is y prime of x? This is y prime of x times xi plus 1 minus xi. What is the most important calculus formula? Taylor series. What this is saying yi plus 1, which is y of xi plus 1 minus y of xi, is approximately equal to phi, which is my slope, so that's y prime of xi times xi plus 1 minus xi. This is my h. This is my phi. This is my yi plus 1. And the rest of the Taylor series I just chopped off. When I chop off a mathematical expression, what type of error am I making? Truncation error. So here we're going to definitely have truncation error. Okay? But it is an approximation. One person knew and everybody just like, wow, she knows that. Good job. So I taught one person something in this class. All right, great. Great job, Masha, as a teacher. So this is our Euler's method. Okay. If I was evaluated as a teacher right now, that would be really bad. Anyway, so first derivative, so basically this dy dx is my slope, and it's f of xi yi based on the equation I'm solving, and Euler came up with this. Euler was a German, Leonhard Euler was a German mathematician. And basically, I substitute that into my original. So this is my algorithm. This is my next iteration for yi plus 1 based on my original iteration. So I start from some point and I keep getting next, estimated next point. Which loop am I going to use when I implement this in Python? I could use either. So as long as I have xi's already done, I can set them up. And I know, if I know where I'm going, I got to stop somewhere. So I'm going to be solving this on an interval. Okay? And I'm going to find all of these x points on that interval. So in that case, I'm going to know how many points I have. So for loop is the best. Okay, I'm going to have a set of points, and I'm just going to go. But I can do it with while as well. Okay? So my new value is predicted using the slope. And basically, this is a linear extrapolation based on Taylor's formula. So here's an example. This one actually looks pretty bad. So if I take in this problem, and we're going to work on a problem that is looking just like this. If I take h of 0.5, and I'm solving a problem between 0 and 4. So I will discretize 0 and 4. So this is going to be my x0, x1, x2, x3, x4, right? And I'm going to start from this point. This is my initial value, and march through. So my y0 here will be given as a boundary condition. I always have to have a boundary condition if I'm solving a differential equation. Okay? So basically, I'm going to start from this point, and based on the slope here, this slope at this point of this true solution that is given with the differential equation is going to send me right there as my next y1. Then knowing y1, I'm going to estimate a slope here using actually this true solution because I have a differential equation for it. And that's a little gentler slope, so it's going to send me to this point next. That's my y2. And then y3, y4, y5. So at every step at y5, I'm using y4 and x4 to get there. And then at this step, I'm using my previous y to get there, and so forth. Okay? And this looks pretty bad because step is pretty large. Okay, 0.5 is a large step. If I actually, if I actually reduce this step sum, I'm going to improve. So this is my step 0.25. I'm getting closer to the original solution. And if I use even smaller, I'm going to get closer. So there is always certain error. What is this error? Okay. So if I do error analysis, I actually start from my favorite Taylor series, right? So I chopped off all of the higher order terms, okay? And that's one part of that error. And I do that at every step. But every step, I also compute based on the previous step, and I had some error built into that already, okay? So when I'm actually at this point here, okay, I have made certain errors coming to here that are propagating. And then I am using a formula that is truncated, so I'm introducing extra error to that. So all of the previous step has a piled up error from before, and the new error is introducing. So that simply has to be there. So there's certain error that basically piles up. Now this error is what we call, it's basically a polynomial with the leading h square. Okay. Once I sum up all of these things that pile up, technically my error is a polynomial with the leading h ultimately. So it's a what we call a first order error. We are not going to analyze these errors, but that's what's often done in numerical analysis, but this is just an introductory course. Either way, as this h gets smaller, okay, I'm going to get closer because my error depends on h. So if the h is smaller, the error will be smaller as well. Okay? And that's essentially because in this Taylor series, I depend on h. Whatever I chopped off is a function of h. Okay. Okay. Well, cool. And of course, we cannot avoid round-off errors that we have because we're using this. We're computing this using a computer. So there is truncation error as well as round-off error. So I have always a round-off error, and then I have this local truncation that happens at every step, and also propagated error from before, and I'm going to call that propagation truncation. So those are the two sources of error in this numerical method. Cool. Without further ado, let's start today. We're not going to go and finish. But first, I actually want you to compute this by hand first. So let's say that I'm computing dy dx is f of xy, and I'm solving this differential equation. dy dx is minus 2x cubed plus 12x squared minus 20x plus 8.5. The reason why I'm solving that one is that my right-hand side actually does not depend on y at all, and this one I can integrate, and I can have an analytical solution. And that analytical solution, assuming a boundary condition y of 0 is equal to 1, is given with this formula. I'm not even asking you to integrate. Okay? To have everything given. So I want you to use Euler's method between 0 and 4 with the step size 0.5. So let's, assuming this x1 or x0 if you want to call it, 0 and 1, I want you to compute the first step based on Euler's method. So that we can complete today. So again, the method is given here. Starting point x1, y1 is 0 and 1. I want you to compute y2 given that step size h is 0.5. So what is x2 and what is y2 using Euler's method? And then on Friday we get to program this. I see happiness on your faces, right? All right. So if you just got awake just now, formula is given here. Given x1, y1, and this rule for iteration, find me x2 and y2. H is 0.5. And then if you're done with that, you can also compute what the analytical solution should be for that point. So you can use your Python or your phone as a calculator as necessary. So this is f of xy, except that here it's really f of x, but it doesn't matter. You just don't. That's the specific function that you're working with. It's a very dumb function of f of xy. And it's so we can integrate it easily, so we can actually compare with analytical solution. That's the idea here. So what is my x2? It's x1 plus h, right? So my x2 is 0.5. So then my y2 is y1 plus this f of x1. So I calculate it for 0, which is really 8.5, times 0.5. Everybody following what I'm doing? Maybe? Maybe not. Let's see if I have it. I think I have it as part of the slide. No, I don't. So basically, if this is y1, which is 1, plus f of x1 is f of 0, and I don't have dependence of y1, so that makes it easier. Here, this is my f, and that's 8.5. Yes? So 8.5 times 0.5 is half of it, so that's 4.25 plus 1. My y2 is 5.25. Yes? Now, in this case, I know analytical solutions, so I could actually figure out what the error is. I can plug in 0.5 in my analytical solution and see how close I am. I'll be actually pretty far. Okay? So next time we program.